In today's lecture, we'll be starting the topic of electric motors. So we will start with a fairly simple machine, which is the DC motor. Now the reason why I will be starting with DC motor is that here you can understand easily what is the principle, how the machine works, and we can later use it to understand the other types of electrical machines. So let's take a look on the composition of a DC motor. It will have several major components. Here we see the stator magnets. So we will see that this is the major component because this component creates the magnetic field from the stator. Here it is shown as a permanent magnet, but we'll later see that this might be a coil as well. On the rotor we have coils and we have the commutator. So this is rotating when the machine works, and the important thing with the DC motor is that the main current that is powering the whole motor is going through the commutator and through the rotor coils. And in order to get the current into the rotating part, we have some brushes. And again, we'll cover in more details the individual parts that you see in this picture. So for now, remember that we need a magnetic field on the stator, and we need some coils on the rotor and then some brushes, a commutator. Let's take a look on the construction first, how the machine is made. I will start with the rotor. You can see the rotor on the left picture here. Now this is a cross-sectional view, so this is not a complete rotor. We did cut the rotor in half so that you can see the actual composition. So here is the shaft. This is placed in bearings on both ends of the rotor so that the rotor can rotate freely. Here this is iron, and we'll later see in more detailed pictures that the rotor sheets are made from laminated steel. So it's a similar type of steel as we have seen for the transformer, and also for the same reasons, because we want to reduce the eddy current losses. And here we see slots with the winding. So this is a copper wire, and this thin layer around it is electrical insulation. So the wire is electrically insulated not only from the other wires in the coil, typically with enamel coating, but it is also electrically insulated from the iron in the rotor. So this is insulation. I will later show you some videos or recommend you some videos where you will be able to see the production process of this kind of machine. You can see that this slot is not completely filled. The reason is because we simply cannot fill it completely with copper. Due to manufacturing reasons, there needs to be always some insulation, and also you cannot fit it completely because the wires would not fit in mechanically. So when you are building a coil, this is what's called a filling factor, and typically the filling factor is, let's say, somewhere around 0.5, 0.6, 0.7. So this means that you have, if it's for example 0.7, this means that if you have 70% of the area filled with copper and the rest is something else. It's insulation, or because we typically use round wires, it's the material between the wires, air or some resin, for example. And those coils are then connected to a commutator. We'll see in today's lecture why this is so, let's now just say that this is the commutator part, and the commutator is a copper ring that has insulated sections. You can see the sections insulated here, and again I will have more detailed pictures a little bit later. And to each individual section you have one coil connected. So this is the rotor. The stator is shown here on the right picture, and you can see that we have coils on the stator. So in this case, in this specific picture, we have 4 coils on the stator. So we have 4 poles, and this means that this is a 4-pole machine. And the number of poles will have an effect on the shape of the magnetic field, and therefore will be able to influence, for example, the torque of the machine or the speed that the motor will have. You can see that here it looks like it's again some laminated sheet, but in the case of a DC machine the stator does not have to be laminated, because in a DC machine the stator magnetic flux is a DC magnetic flux. But in the rotor we'll see that this will be an AC flux. So in the rotor we need laminations because we want to reduce the eddy current losses, but in the stator we don't need that. But for example, due to manufacturing reasons, you may do this also as a laminated piece, because it's usually simpler to produce with one operation on a press, for example, the sheet for the rotor and for the stator as well. So you may see also DC machines that have laminated steel in the stator. You can see that the coil is made here from copper wire. Again, it's enamel coated so that the individual wires are insulated from each other, and they will be of course insulated also from the iron that we have in the stator. And again we'll see more detailed pictures in a minute. So here we have a more detailed picture of such a rotor. It is also very often called an armature. So if I will say armature or rotor, this is equivalent name for a DC motor or even for an AC motor that we'll see later. So here you can see clearly the laminations in the rotor sheets. So this is made from silicon iron, silicon steel, which is with a high content of silicon, let's say between 3 and 6% approximately. The sheets are cut either with a laser beam, with a water jet, or if you have to produce larger series, then you have a die and you press that in a press with a die. And the thickness is typically, let's say, 0.35 millimeters, so 350 micrometers. It could be 0.5 millimeters, could be 1 millimeter. It actually depends on the properties that you want from the magnetic circuit. We follow the same logic as we have done for transformers and for the magnetic materials. So if I want to reduce the losses, the eddy current losses, I would use a thinner sheet so that I have a lower loss. But on the other hand, it will be probably more difficult to handle very thin sheets. So I cannot go to something like 50 micrometers because it would be like a sheet of paper, and during the manufacturing process it would probably I would probably waste a lot of material. So there is a trade-off between the magnetic properties and then mechanic properties, because from mechanical perspective you would like to have solid piece of iron, but a solid piece of iron in terms of magnetic circuit would have very high losses. Then it's pressed together in a press. Again, I will recommend you a video where you can see that. And you can see that in the slots here we have the copper wire. Maybe this is a better picture here. So we see that the copper wire runs along this, and well, it's running in this slot, all the coil, and then on the opposite side it would run in a similar slot. You can see that sometimes we have a skew on the slots, so sometimes they are aligned in the axial direction, like here and here, but here we have a slight skew. The skew is there in order to reduce the torque ripple, and we'll be talking about it also during our lectures. And here we can see the commutator. So this is a copper ring. It has individual insulated sections, so here we can see one section, another section, and so on. And we can see that there is always one coil connected to the section of the commutator. And here is the shaft, so here you would have one bearing, and here you would have another bearing. And this would be the output shaft, so this is where you connect to your load. So for example, it could be a fan, it could be a servo, whatever you want to drive, it could be a wheel, for example. In some cases, such as this one, you use the DC motor to drive some mechanism, such as a ball screw, for example, or a motion screw. So you can see here we can have the thread directly on the same shaft. So then this is the motor. Here you would have a bearing on one end and the bearing on the other end, and here you would have some worm gear, for example, and this would act like a gearbox. Here is a more detailed picture of the rotor laminations. So we can see the thin sheets. They are aligned together so that we can insert the copper winding inside of this slot. And here you can see where the shaft will be pressed. So this is produced either by a die on a press, if you want a really large series of the motors. If you are producing, let's say, smaller series, maybe up to some thousands of pieces, then it will be cheaper to cut this on a laser beam today, or water jet, and then press that together. And in the video that I will send you a link, you will see that how this is produced on a die. You will see that they will then insert insulation here in the slot, so that the wire will not get damaged and we will not have a short connection between the wire and the iron in the rotor stack. By the way, this is quite often called a stack. So if I will be talking about rotor or stator stack, this is what I have in mind, a packet like this. Here we see a more detailed picture of the commutator. So we see that this is a copper ring. It's manufactured typically by turning or by milling, and we can see that this is insulated from each other, so it's like a copper pipe, and here it has cut slots, and this insulates electrically the sections of the commutator from each other. And you can see those slots here. Those slots are there to solder the wires from the coils. So this commutator during manufacturing is pressed with a press or on a drill if it's like a small series, and on the shaft, and then you need to solder the copper wires from the coils to those parts of the commutator. This is a detailed picture of the stator. In this picture it is made as a solid piece of iron. So you can see that this is a solid piece of iron. Here there are two screws which fix this is called a pole, to the stator. So this is like a pipe with large diameter, cylinder, and during the manufacturing they make some threads and they screw this in the stator, and this is the copper wire coil. Again, enamel coated wire. It's electrically insulated so that you don't have a short connection between the wire and this. This needs to be made from a material that is magnetically conductive, so it's typically iron. And this could be cast iron, although it does not have such a good properties as silicon steel in terms of magnetic circuits. If you want to produce like a single piece, you can cast it and it's simpler to produce. The reason why we can use a single piece of iron here is that in a DC motor, the magnetic flux in the stator is DC flux, so it's not variable, and therefore we will not have any eddy current losses or hysteresis losses. And now let's take a look on how the magnetic circuit looks like in such a machine. So here you see a similar core that we have seen in the previous picture. Here is the cylinder around it. This is my frame of the motor. So it acts like a frame in mechanical terms so that it holds everything together. But at the same time it acts also like a part of the magnetic flux, and it guides the magnetic flux inside. So therefore it needs to be from some magnetically conductive material. This piece with a coil here, this is the coil here, 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 and there. So again, this is an example of a 4-pole machine, and this is what's called a pole piece. You can see that here we have typically like a cylindrical section where the coil is wound. So that's this part here, would be over there, and well, it's either cylindrical or it's a rectangular. Well, in this case it will be a rectangle, so the shorter side will be here and the longer side will go along like this. And then you can see that here we have this extension, this pole piece, and this is what is used to guide the magnetic flux evenly in the air gap. We will need an air gap between the stator and the rotor, which will be here, because we want that the rotor can rotate freely in the circuit. So it cannot be very tight connection. The air gap in the machine is typically something like 0.5 millimeters. So we try to maintain the air gap as small as possible. And we can see that if we power the coil with DC current, we will get magnetic flux. And the magnetic flux in this picture is shown by those flux lines. So for example, in the case of a 4-pole motor, 2 poles will have north pole, those two, and 2 poles will be south pole. And you can see that all the coils are connected in series. So here we have the 2 terminals from what's called a field winding, and we supply DC current to this field winding. And you can see how this is connected. This goes like this, and then it creates one polarity of magnetic field. Then we go over there. This creates another polarity, and then we go over there, and basically we change between north and south poles in the orientation of the magnetic flux. We can see that the magnetic flux flows like this. It's created in the coil, it flows through the pole, it flows through the frame because it's ferromagnetic, the frame, and then in our particular case of a 4-pole motor, it's closing like this. Here in the picture we don't have the rotor, so that we can see properly all the components, but in the real motor here that's where you would have the rotor. And the rotor is also made from a magnetically conductive material, so we have what's called a closed magnetic circuit. It means that there is no air gaps, or at least very small air gaps that happen in the circuit. So virtually everything in the circuit is formed with a magnetically conductive material. And only where you really need it, you have an air gap. So you will have a small air gap between the pole pieces here and between the rotor. So there will be like a small air gap between the rotor and the stator. The smaller you make the air gap, the better magnetic properties you will get from the motor. So in terms of magnetic circuit, we try to have the air gap as small as possible. But on the other hand, we cannot make it like very small. We cannot make it like maybe 10 micrometers. That's not possible because we will have manufacturing tolerances. We will have temperature expansion of the material. So if we make the air gap too small, we risk that the problem will be mechanical. The rotor may hit the stator, we will get a blocked rotor, or even we may destroy the machine. So from mechanical perspective, you need to make the air gap larger. So there is again a trade-off between the mechanical properties and manufacturing capabilities and the magnetic properties. So the normal size of the air gap is let's say under 1 millimeter. The smaller the better, so something around 0.5, 0.3 millimeters. If you make it too small, then it may happen that your motor heats up during operation, the material expands, and the rotor may even hit the stator. So remember that for all electric machines, not only for DC motors but for AC machines as well, we are operating with a closed magnetic circuit. Now, in order to simplify the following drawings that I will show you, I will omit this closed magnetic circuit because it would prevent us to understand the main functionality. But keep in mind that without the closed magnetic circuit, the machine would have very, very bad properties. We have seen when we discussed magnetic circuits that the presence of iron is very important. The iron guides the magnetic flux, and if we do not have this iron or any other material that guides the magnetic flux, we will have air which magnetically has very bad properties. So electric machines, they really need to use closed magnetic circuit, unless you're building like a very special machine, for example, where you require some low torque, for example. But if you want to build like a normal machine with let's say good enough properties, you really need to use a closed magnetic circuit. So let's take a look on how the DC motor works. And if we understand this, you will be able to understand all the electric machines in the future. Now again, let me remind you that a closed magnetic circuit is not shown in this picture, but it is required. So in this picture I have omitted all the iron that we have in the circuit, but there needs to be an iron in the rotor, so there would be a stack of iron here, and there would be a stack of iron around as the stator. So we can see the principal pieces of a DC motor. We can see here on the left and on the right, this is our permanent magnet. So it's either like a really permanent magnet, or it could be a field winding. So you can find some smaller motors which are called permanent magnet motors, which have permanent magnets here that create the magnetic flux. In general, this is applied for smaller machines, or for machines that you don't need to change its properties somehow. But if you do need to change, for example, the speed or the torque or some parameters like this, you may need to adjust the strength of the magnetic field. And this is where the field winding comes in play. So the field winding is this. So it's a coil, and if I change the current in this field winding, I will be able to change the properties of my machine. So typically larger motors, they are equipped with a field winding like this, and you can adjust the current and change whatever you want from the motor. So let's imagine that now this is some kind of magnetic field, either with a permanent magnet or as a field winding. So we can see here we have the South Pole, here we have the North Pole, and obviously there would be some magnetic flux between those two poles, which is shown here as this flux density B. So this is my flux density. We've discussed how much that can be. It is a function of the materials. So for example, if I take silicon steel, this might be something like 1 or 1.2 Tesla, for example. Then we have the rotor coil here. So this is my rotor winding, and again, for simplicity, I showed this as a single piece of wire. But in reality, this would be a coil of a thinner wire, and it would have some number of turns. And this is placed in the slots on the rotor. So the coil is this. So this is, you can see that here we have probably like maybe 20, maybe 50 turns, and it's all then connected to the commutator over there. The commutator connects the coil and the brushes. In my picture, I have the commutator shown as with two sections only. Again, this is for simplicity. Such a motor would not work very well, but a more complicated commutator would cloud this picture. So this is like only to explain the principle. And then we have a brush. The brush is mounted on the stator. So the brush is stationary. It is pressed against the commutator with a spring, and it makes an electrical contact between the brush and between the commutator. The brush is typically made from carbon. So it's like a block of carbon. On this side here, on the stator, on this side here, you have a spring that pushes that against the commutator. So carbon is electrically conductive. It is also a very good lubricant, so there will be lower friction between the commutator and the brush. And we can see that the brush is then electrically connected to a power supply. So here we have a DC power supply that powers the whole circuit. So my current from the power supply flows through the brush into the commutator, then it flows through my winding like this on the rotor, and then again into the commutator, to the brush, and back to my power supply. So we can see that the main current flows through the armature, through the rotor. So this rotor is called an armature. So if, for example, our nominal current of a DC motor would be 10 amps, then all the 10 amps would flow like this. They need to go through the brush and through the commutator. On the other hand, if we have a field winding on the stator that creates the magnetic field, the current here is typically much smaller. So if this is 10 amps, this might be something like 100 milliamps, for example, or 50 milliamps. So one of the, let's say, features of the DC motor is that all the current that creates actually the torque needs to go through the brush and through the rotor itself. So now we have a current that is flowing in my rotor, and this is a wire with current I, and we have placed this wire in a magnetic field. So we can see that there will be a force that starts to act on my wire here, on this part of the coil. Now with some calculations, we can find out that the direction of the force will be like that, because here we have one orientation of the magnetic field, we have one orientation, given orientation of the current, and hence the force will go like this. On this side of the coil, we can see that we have the same orientation of the magnetic field, but we have a different orientation of the current, so the force will go downwards. And the force here and here, that's what will create as the torque. Now the force will obviously be proportional on the magnetic flux density, so B. It will be proportional to the current I, and it will be proportional to the length of my conductor, which is not shown here, but let's say this will be L. So the longer the wire, the longer your rotor, the larger the force. The stronger the magnetic field, the larger the force, and the larger the current, again the larger the force. So if we want to adjust the properties of our machine, we can either make it longer, so it will have larger torque at the end, or we could use larger current, but here we are limited, of course, by heat, how much current we can actually push through without heating it too much. Or we could use a stronger magnetic field, and again here we are limited with the material that we have available and its saturation density. Remember that we know this equation from physics. This is a vector multiplication, so this will give us also the direction of the force. You can see that here the I and L, they are oriented in the same direction, but the B, the flux density, is perpendicular. So when we are in this position, we see that we have some force that is acting on my coils, on the rotor. So the rotor will start to move. This part of the coil will move up, and this part of the coil will rotate downward. So this will move. This rotor, like I have it now, will start to rotate clockwise. Now let's imagine that we have somehow different position. So now I have rotated the rotor by some angle theta, and here we can see, okay, we are still in the magnetic field, so our force will have this orientation still, like this, perpendicular. But now it will have one component that is perpendicular to my coil, like this. So the plane is rotated under the angle theta, and the force that actually creates the torque will be my force times cosine of theta. So I will continue rotating it like this until I reach this position. Now I have the angle theta 90 degrees. Here we need to know two things. One thing is that if you see this equation, f times cosine of theta, then if theta is 90 degrees, then the force needs to be 0 because cosine of 90 degrees is 0. So when we are at 90 degrees, the force is 0. That's one reason why we have 0 force. Another reason why in this position we have 0 force is shown here in this picture. Now you can see that this brush shorts the two commutator sections together. So at this particular position we would have a short connection on the power supply, and the current would go directly like that through those sections and would not go into my coil, so we would have 0 current in this position. Now by rearranging this and making a larger number of sections, we can actually remove this problem of the short connection. So in a real motor this will not happen, but we will still have 0 force because at this particular orientation we have theta of 90 degrees. So we can see that if we would build such a very simple motor with only 2 sections on the commutator and only 1 coil, it would not work very well because it would most likely stop in this position. I'm saying most likely because here we will have to our advantage the mechanical inertia. So if this starts to rotate and it's moving like this clockwise, then in this particular position it will still have some inertia and it will move like that. And it may happen, and it's often the case, that it will overcome this position where the force is 0, and it will go to another position where the force again starts to act and has the proper orientation and it's not 0 as well. So in the design of a DC motor we are accounting also for the inertia of the rotor. And of course, in a real motor, we will have more sections and more coils on the commutator. So the more coils you will have, the lower the torque ripple is of your machine. If it would be only like a simple machine with 2 sections like this, basically you would have maximum torque at this position, calculated as F times the radius of your rotor, and this would be your maximum torque, and then your minimal torque would be 0, which you would have here. So it would not be like a very good motor at all. When we overcome the inertia, now what will happen? We are at this position, and now note that suddenly this commutator section has changed its polarity. If I follow my picture, if I am for example here, then this section on the left, now it's connected to plus polarity. Here short circuit, this is the same section, and now here this section is suddenly connected to the negative pole of my power supply. So the current has changed polarity. We can see it here also by the direction. So suddenly current is flowing like that in this section and it like this in this part of this coil. So the commutator acts like a mechanical switch that allows us to change the polarity of the current. And we can see why. Here I have changed the polarity of my current, and again the magnetic field has still the same orientation, so it's from the North Pole to South Pole. And if I have made the vector multiplication like this, you will find out that the direction of the force is correctly oriented, and this will continue to rotate with the rotor. So during all the operation, when I have clockwise rotation, my force that I have in the rotor is oriented in the same direction. So clockwise here, well, 0, but in the other position it would be oriented clockwise, like that. So this will start to create the torque. And again, this is rotated with some angle theta, and the force and the torque that I have is given as force times theta, cosine of theta. Okay, so this is how the DC machine works. So commutator acts like a mechanical switch that allows us to switch the polarity of the current in coils. Again, in a real motor you would have multiple sections, and this would allow you to reduce the torque ripple of your machine. Let's take a look now on a cutaway view of such DC motor. Here we can see the armature. This is my rotor. This is the iron that we have in the rotor, so laminated steel, coils, and here we have a commutator. So you can see we have many sections in the commutator. In terms of torque ripple, the larger the number of sections, the smaller the torque ripple. But again, there is a limit because you cannot fit too many coils in the rotor because they would simply not fit. And also the commutator, you cannot make the sections too small because then you would not be able to make a proper contact between the commutator and the brushes. Here we see what's called a brush assembly. So the brush is typically made from carbon. For very special machines, for example for measurements, you can find that the brush is made from thin silver wires. But for normal motors, this is made from carbon. And then of course we have the bearings at both ends. So here a ball bearing, and here there will be another ball bearing at this end as well. And the frame here, the frame holds the stator. So this is the coil. You can see here this coil. This is creating the magnetic flux. In this case, it's a motor with field winding, so no permanent magnets, and this magnetic flux is created by the field winding in the stator. Here are a few examples of such DC motors. So DC motors are produced from really small ones up to the very big ones. You can see here it says, let's say, more than 1000 watts, 1000 kilowatts motor. You can see the size. You can see this is the commutator, and here you can see the slots, and every coil in the slot would be connected to its individual section on the commutator. So DC motors are still used, although they are largely replaced, for example, by induction motors due to efficiency and reliability. But you can still find such large motors, for example, for rolling of steel or milling, some applications like this. We'll see that they have like a very large advantage, that you can very easily control the speed and torque of your motor. A few more examples. Again, I've chosen larger machines so that you have an idea that a DC motor does not have to be just very small. That's something you have in a toy. But industrial applications, they are still using many DC motors, and they can have hundreds of kilowatts, maybe megawatts of electrical power. This is an example how it looks like during the production. So you can see here we have this white stuff, that's the insulation that insulates the wires inside of the slots, and that's where the coils will be placed. So you can see this will be the sheets, and the worker will then insert those insulated sections of the wire inside of the slots. Now this is a smaller motor. They were saying 500 horsepower, so it's still quite large, but would be something like 400 kilowatts, but definitely larger than those motors which have few hundred of kilowatts. In the back here you can see the enamel coated wire, so it's typically supplied in coils like this. And then if you are building like a small machine, you probably will wind this manually, or if you are building like a series of machines, you will have specialized machines to wind your coils. So let's discuss in more detail the magnetic field that we have actually in the DC motor. What you see here on the left, that's the main magnetic field. So this is a magnetic field that is created from the stator winding. And in this picture we have an example if it would be a two-pole machine. So we have one north pole and we have one south pole, and obviously here there would be the coil like that. So the coil would be wound like this around the pole piece, and then another coil would be like that, and they would be connected in series, and this would be my power supply voltage, so for example plus and minus like that. And you can see how the pole pieces are making the magnetic field uniform. So here we are assuming that we have a uniform field distribution. So I will probably for next time I will prepare a simulation of this magnetic field with some finite elements, so that you can see what's actually the shape and how does it change if I change the shape of the pole piece, for example. So remember that this is only the field created from the stator. We have a second field there, and this is the magnetic field from the rotor, from the armature. And in the armature we have wires that run in the perpendicular direction to our plane. So on one side we have the current that's going into the plane, so this is going like into the plane, and this is coming out from the plane. So if I go back to my picture, which, well, for example this one, then this was this part, current going into the plane, and this is this part, the current going out from my plane of view. But this is still current, so it means that the current will create its own magnetic field. So we have a magnetic field that has this shape, like this. And in the machine during operation, those two fields will interact. And this is what's called armature reaction. So we can see the final magnetic field here. We can see that the field lines from the stator have changed the shape. They have like a slight angle like this, like that in my picture. And this is what's called armature reaction. So armature reaction is the distortion of the main field due to the armature magnetic flux. And you can see this small skew, this non-zero angle. Initially it was like perfectly horizontal. Here we have some small angle from the horizontal direction. And if we want to compensate for the armature reaction, we need to rotate slightly the brushes of the DC motor so that we compensate for this effect. Here we can see why we need to do this. It should not be major reaction, but I will just go back to PowerPoint and put this back. This is obviously armature reaction. Here we see few pictures of the magnetic field in the machine. So here we have the North Pole, and here is the South Pole. So this is like a linear version of the chart, so that we can plot it. But obviously this would start somewhere here, and we would like make a chart like this, like a circular chart, so that and then we make this simply in a plane. So we have one position, you start somewhere here and you move. This is basically the cylindrical coordinate that you have in the cylindrical chart. You can see the pole piece here, simplified picture. You can see the field winding. So this is the field winding that creates the magnetic flux, and this is the field density distribution as created only by the field winding. So under the pole we are assuming that we have a uniform distribution like this. So this is a constant flux density under the pole, like that. And obviously between the poles we need to switch between one polarity and another polarity, so there will be some transition. This will depend on the shape of your motor, but let's say it's linear like that. And if there would be no armature reaction, we would orient the brush in this position, like here and like there, and like, well, this brush is the same brush like this one. You can see how this is oriented. The brush is oriented in the position where I have zero flux density, so like that. Now as we introduce the magnetic field created by the rotor, we can see that this position will shift somehow. Here this was the original position. Well, at least this was the original position, and we had disoriented like in this zero magnetic flux. But this is the magnetic field shape when you have combined the magnetic field from the rotor and from the stator. And we can see that now we have a different position like this. And we need to place the brush in this position like that, so that we have this position where we switch the magnetic field orientation, so where the magnetic flux density is zero. And this is what's called a shift in magnetic neutral axis. So originally when the two fields were combined, it was for example at this position, and then we needed to shift it to that position. Now this position is this field density was only where we had the stator field, but if we then add the rotor field, it will all shift like that. So this means that we need to position the brushes to this neutral axis like that, so that we don't change the magnetic field when it's not zero. Otherwise we would have for example sparks on the brushes, and it would not work as good as when it's aligned properly with the neutral axis. So this is another way how we can actually neutralize the effect. So instead of turning brushes, we can have what's called an interpole, and this is like a smaller magnetic pole that is connected in series with the main winding. So we have two poles like this, North Pole and South Pole. and they provide the main torque. And here we have smaller poles, they are connected in series like that, and they neutralize the effect of armature reaction. So this is like more if you would like to design such a motor, but in terms of let's say our subject, you should at least know what's the armature reaction, and if we would have lab classes, you would learn how to rotate the brushes and how to measure this armature reaction. Let's take a look now on the power flow that we can expect in a DC machine. So on the input we will have some electrical power. Now this is a DC machine, so electrical power is simply obtained by multiplying voltage times current. So this power flow diagram will also show us the losses and their ratios in the machine. So our current, our power, is going first into the winding, so to the copper coil, and we will have joule losses in the power coil. So those losses are proportional to the resistance and to the second power of current. Then this power is being transferred through the air gap, and then we will have some other losses in our machine. We will have some losses in the magnetic material, so this will account for the hysteresis losses and for the eddy current losses. So this is influenced by the material that you have in your machine. Then obviously we will have some mechanical losses. We'll have some losses in the bearings, for example, and then we will have some what's called stray losses. When we discuss magnetic circuits, we've seen that not all of the magnetic flux will flow in the iron, and there will be some small magnetic flux that is flowing around it, so that's what's called stray losses. And also in those stray losses we may include some other losses that are not accounted for in those components. So sometimes you find it like this, like a stray losses, or you may find this like another symbol here, and this would be some other losses. What can it be, other losses? Well, this could be, for example, losses due to friction with air. So it's called very often ventilation losses. And if this is like a higher speed machine, this might be quite significant. But for lower speeds machines, let's say 1000, 2000 RPM, the ventilation losses would be very small. Or this might be another loss that is created, for example, in a fan. So you have a motor, like a DC machine, it's rotating, and you need to cool down those joule losses and other losses as well, of course. So you need to provide some airflow in the machine, and therefore you are installing a fan directly on the shaft, so that when the motor rotates it will create its own airflow and it will cool itself down. So this might be also accounted in this other losses. And on the output, when we subtract all those losses, we obviously will have some mechanical power, which is given as torque times angular speed. Obviously we can calculate efficiency, so if we know the output power and input power, we can calculate the efficiency. As for all electric machines, the efficiency will be dependent on the size of the motor. So if you have like a smaller machine, it will have lower efficiency, but if you have like larger machines, few hundreds kilowatts for example, it will be much more efficient than a smaller machine. And of course this depends also on the materials. It will depend on the magnetic core, it will depend on the bearings, it will depend on the cross-section of the wires, so it will depend on many factors. Now let's take a look on some circuits that we will use to describe the DC motor. So this is like a generic picture. This coil will represent the field winding. So this inductor represents me electrically the stator. So we have some current that is flowing through this winding, and I could of course add some resistance as well. And this circuit on the left represents me the rotor. This black box here, this represents me the brush, so this is the brush. And I will need some power supply that is connected to the rotor, to the armature. There will be some current, and I will need, in this case, another power supply. Let's call that UB, for example, so that here I can supply some current in the field winding. And this field winding will create me magnetic flux. So the magnetic flux phi will come from the field winding, will go through the armature, and together they will create torque. So how can we actually connect this in a circuit? But we can use two separate power supplies. So we can have one power supply for the armature with some voltage, let's call it VA for example. This will give us some current IA in the armature, and we can have a separate voltage supply, let's call that VB for example, for the field winding. Now this is what's called a separate excitation. So we have a separate power supply for the field winding and for the armature. Now a second possibility is that you use one power supply and you connect those two windings in series. So you have the field winding, and then the same current is flowing through the field winding and through the armature as well. So we have the same current, and let's call this current for example IA, because it's flowing through the armature as well. And this is called a series connection. And then those two connections, they are somewhat combining those two connections together. So here we have a single power supply, let's call it VA, and we are supplying some current in the armature. Here we have a variable resistor, and hence we are able to adjust the current that's flowing through the field winding, so this would be IB. This is called a shunt connection, so we're shunting this from a single power supply. And the last connection combines the series connection with the shunt connection. So here we have a variable resistor with the field winding. We are supplying that from a single power supply, but then we have an additional winding that is connected in series. So here one part of the current flows like this. This is the current through the armature, IA, and this will be the current, let's call it IB, that will flow through the field winding. And this is called a compound connection. Now every connection will have different properties, also in terms of mechanical characteristics. So we will discuss only case A and case B, and the other cases are like combining the advantages of those connections in some applications. So let's take a look first on the case where we have separately excited DC motor. So this means that we have one power supply for the armature and one power supply for the field winding, and they are separated, so we can have different voltages on the armature and we can have different voltage for the field winding. So this is my field winding here. It has some inductance and it has some resistance. And the field winding is creating magnetic flux. Now if we write an electrical equation for this circuit, it's nothing else than an RL circuit. So if I describe that with a differential equation, it's going to be this one. So we can see that well, this is the electrical equation. We can use this equation even in transient states, because here we have the differential equation. So if we solve the differential equation, we'll get the value of what's IB and what is the function of IB versus time, for example. And we can create a similar circuit also for the armature. So here we'll have the inductance of the armature and we have the armature resistance. And this circle is the voltage supply that is representing the induced voltage. Remember that we have a coil, and this coil is rotating in the magnetic field. So it was the magnetic flux that is created from the field winding, and this coil is rotating. So in electrical terms, this means that we will have some induced voltage in the coil, and the induced voltage will definitely be a function of angular velocity, because if it's standing still, we'll have zero induced voltage, but as it will rotate, the induced voltage will increase. So Vi will relate us the electrical properties to omega. If we write the electrical equation for this circuit, we see that again it's an RL circuit. So we have a differential equation where the voltage on the inductor plus the voltage on the resistor plus Vi needs to be equal to Va, and that's this equation. So we now have two electrical equations that describe the armature and the field windings. Now we need to include somehow the properties of the magnetic circuit, because here we have a magnetic circuit. This is creating the magnetic flux, and we have seen that it will be described with the hysteresis curve. So we are looking for the dependence between the current IB, which is flowing in the field winding, so this is current IB, and between the magnetic flux. So in general, it is a formula like this. We're looking for some function that describes that phi depends somehow on IB. It is a magnetic circuit, so we have a hysteresis curve like this. So this is the current. So for example, if I choose some current, let's say maybe like this current would be in the field winding, then from the hysteresis curve I can read that I would have this value of B, which is proportional to the magnetic flux. Now this field winding, it's supplied with DC current, So okay, that's great. We have DC current here, and we read one value of magnetic flux. So at the end, it will be some constant times current IB. However, this is not a linear function. We see that it depends on the position. For example, if I place it here and like this, it would be more or less linear dependence. But if I choose a point like this, then I would have a different relation, so it's not linear anymore. But the advantage of a DC motor is that it operates with DC magnetic flux in the stator, so I can replace this with a constant. So now we see that phi depends with a constant on current IB. The induced voltage, that's now we're talking about this part. Now the induced voltage will depend on angular speed. So Vi will be a function of omega. So the larger the angular speed, the larger the induced voltage. It is a coil that is placed in a magnetic field. So the stronger the magnetic flux here, the larger the induced voltage. So it will depend on phi, directly proportional. And then it will also depend on how this magnetic circuit is made. So on the construction. So we can write this equation. The induced voltage is directly proportional to omega. It's directly proportional to the magnetic field. And this CSS, this is the constant of the DC machine. So this constant describes me basically the construction. It's telling me how will the omega and phi transfer to the value of induced voltage. So this is a constant value for a specific machine, but you can change omega as you run faster or slower, and you can definitely change value of magnetic flux, because remember that magnetic flux was a function of current IB. So the advantage of a motor with separate excitation is that I can change the current IB, and hence I can change not only induced voltage, but later we'll see that we'll be able to change torque as well. How about the torque? Well, it's clear that the torque will depend, it has to depend on current, because the larger the current, the larger the torque, so it's here. It has to depend somehow on the magnetic field strength, so this is covered with the value of phi. And then it has to depend with on the construction. So what is the air gap, what is the flux density, what material do I use, what are the dimensions, and so on. So this is again covered with a constant, same constant CSS. So we can see that the electrical torque that I produce is directly proportional to the construction, but to some constant. It's proportional to the magnetic flux, and it's proportional to the current. And the last equation that we will need is the mechanical equation. So the electrical current torque that I produce is given, well, this is what I produce from my current, from my motor, and this needs to be in equilibrium with the load torque. And then this B and J, this is the B is friction, and J times derivative of omega, this is the inertia. So now we have several equations that we can use to describe mathematically our DC motor. So we have the electrical equations here for armature and for field winding. We have the equation for the magnetic circuit. We have an equation for the electrical torque that we are producing. and we have an equation for the mechanics. So this set of 5 equations creates a complete mathematical model of a DC machine. So if you know the constants, for example, if you know what is RA, what is LA, and so on, what is friction, what is inertia, you can model this, for example, in MATLAB or in Simulink or any other software, and you can see what are the properties of your machine. From this you can calculate the dependence between speed and between torque, for example. You can calculate the efficiency. You can calculate the behavior in transient operations and so on. You can calculate what happens with my current or with my speed if, for example, I change the load. So all this is possible with this simple mathematical model. You can see that we can, this model is universal, but very often we try to simplify the calculations. Here we have 3 differential equations, so we would need to solve this as a set of differential equations. Well, not a set, but like separate differential equations. We can make some simplifications if we want to calculate this in steady state. And by steady state here I mean both electrically and mechanically. So what will happen in steady state, if you have mechanical steady state, now in mechanical steady state, let's do this. In mechanical steady state, it means that the omega is not changing, omega is constant, and this will remove me the inertia. If I am in electrical steady state, this will not be there because derivative of current will be 0, and this will not be there either. So in steady state we will have only a simple algebraic equation for the armature, a simpler algebraic equation for the field winding. Well, this was already an algebraic equation, this was as well, and the mechanical equation the same. So we will get rid of the differential equations, and we can calculate that omega will be a function of the armature voltage minus the drop on the armature resistance divided by the constant times magnetic flux, and torque will be again a linear equation, current, flux, some constant. So now let's take a look on those 2 equations, and we can plot the torque speed characteristic of the machine like this, because we can see, okay, omega will depend somehow on my parameters, and torque will depend on my parameters as well. So how will this look like? Well, in steady state, if we are increasing the torque, now what does it mean? I'm increasing the load torque. Well, this is load torque. I'm increasing the load torque. If you take a look on this equation, it means that if I'm increasing the load torque, now my speed needs to drop. So I load the machine more and it will decrease its speed. So this is shown here in this chart like this. It will be a linear dependence, because in steady state we don't have this. So we'll have omega mechanical will be the electrical torque that I produce minus this, and let's say now this will be some losses as well. So basically the torque that you produce has to be equal to your load torque. The more you load the motor, the larger you will have the current here, IA. And the larger the current, the larger the voltage drop on your armature resistance, and hence the smaller the value of omega. You can see on this equation, now this is a linear equation, and this is a linear equation as well. We have some constant power supply voltage VA. This will be constant in separate excitation motor because phi is created by the field winding and it's not dependent on the current in the armature. So we have a linear equation. It's some constant minus something, some linear dependence. You can see that here RA will be a parameter of my line. So if I plot RA1, for example, like this, then this will be for another resistance, RA2, and this resistance will be larger than RA1. So by changing the value of my armature resistance, I can create a different characteristic of my motor. Say, for example, for some reason in my application I would need that it's behaving like that. So then I can add an additional resistor. It can be a fixed resistor or variable resistor, for example, in this circuit. So I may add an additional resistor, let's call it RP, for example. And by adjusting this resistor, I could change the properties of my motor. Or I could do similar thing in the field winding. I could add another variable resistor here, and by changing the current in the field winding, I could change magnetic flux, and then it would change me again, it would change me the torque, and it would change me the speed. So if you have a separately excited motor, it is fairly simple to change the speed and the torque. Of course, they are both related. You can see here, if I change the torque here by changing, for example, current IA, I will change the current IA also in the speed equation. So it will have an effect on the speed that the motor will have. And also if I change the magnetic flux, for example, if I make it larger here, I increase the magnetic flux in the field from the field winding, I will obtain larger torque, but here I will obtain slower speed, because here I'm dividing that with phi. So how can I actually control the speed of my motor? We have this equation. So first of all, we can vary the voltage from my armature. So if I use a larger power supply voltage for the armature, I will increase the speed. I can add a variable resistor in the armature, and by increasing the resistance I will decrease the speed. I can change the armature current, and if I make a larger current I will decrease the speed here. But on the other hand, if I use a larger current, I will increase the torque. And the fourth possibility is that I can change the magnetic flux. And I can do this by varying the current in the field winding. But again, trade-off is that by changing magnetic flux, I will change the flux. I will change the torque that I can create. So there will be two ways how we can actually change the speed of a DC motor. So how can I vary the voltage? Well, I can vary it with what's called a pulse width modulation. And here you can see the typical connection. So this is my motor, this is my DC power supply, plus and minus, and we will use a transistor to switch that. Now this current is going through the armature, so this is used to control the armature current. Here we can see the electrical equation. It's a differential equation, it's an RL circuit. So what will happen in the circuit is that if I change the voltage on the motor, for example like this, Now I will make it thinner like that. This is voltage, let's call it VG, which will be here on the gate of my transistor. So with PWM, what I'm doing is that I'm switching the voltage on and off. If you look on this differential equation, this is my voltage VA now, so this is the voltage like there, but proportional, because VA would in fact be over there. But it will have the same shape, it will be a rectangular wave. And now, what about the current? Now current in my circuit, now remember that this is an RL circuit. So current cannot change abruptly, and the current will be an exponential. So I turn the voltage on, current will ramp like this, an exponential, and then here it will decay, here it will ramp, exponential function, here it will decay as well. Now remember that here I'm changing the duty cycle, so this is T and this is T on. I'm changing the ratio between T and T on. And here I have like a smaller width of my pulse, so it will ramp up only to a smaller value. So it's on for a shorter time and then it's off for a longer time. So do something like this, and then it will do something like that. So I'm changing the current. If I calculate the mean value of my current IA, here it will be smaller and here it will be larger. And that's what we want here. We see that in our equation over there, the speed is a function of current. So if on the average I will have larger current, I will have a larger speed, and if I have lower current, I will have lower speed. And with the torque, it's the same. So by using PWM, I can very easily change the speed of my motor. We have mechanical inertia that will prevent the motor from stopping. So what is happening is that if you turn it on for all times, like you have permanently on the motor, it will turn with the maximum parameters, some given torque and some given speed. Now if you use PWM, you change the duty cycle, so for example 50%, it means that the motor will be 50% of the time on and 50% off. The frequency is important. Obviously if you would turn it on like every few seconds, then it would not work very properly. But the frequency of this, which is 1 over f, this frequency is typically in the order of few kilohertz. So you turn the motor on and off several thousand times per second. Due to electrical and mechanical inertia, it will turn, but you are able to control the speed because you are changing the current that is going through the motor because of this equation. Okay, that's all for today. We'll discuss other topics next week.